quote on this computer. So today I wanted to talk about, so we discussed minimization last time, and today I want to talk about finding solution of the function or zeros. So of course, there's many routines in scipy provided to find the solution of zero. We were going to use some general purpose solver, which is called Fsolve, which solves f of x is 0, where x can be vector. So some routines allow you to solve only one-dimensional problem, which is relatively simple. The multidimensional problem is much harder, and there are only very few routines that can do that. Fsolve is one of them. Now, I quickly checked what this Fsolve really is, and here is some description. So it is based on Powell's hybrid method, as implemented in Minpack library. So Minpack is a library which is written in Fortran, and we can, in principle, download the Fortran code, but Python or scipy has this done for us. Now, if we want to solve more precise, we want to see more precise documentation about this Minpack library is available here. But the important point is to understand roughly what is Powell hybrid method. And here is description. So Powell's Doggle method, which is also called hybrid method, attempts to minimize the sum of the squares of the function values. So if we have one-dimensional function, then basically it tries to minimize x squared, basically. But if we have multidimensional function, it tries to minimize x squared plus y squared plus z squared and so on. It does this using a combination of Newton's method and steepest descendant method. This is so-called trust region method. This means that every step moves the current point to within a finite region. This makes the method more stable than the Newton's method itself. On the other hand, the fact that the method is in essence a specialized minimizer means that the algorithm can be stuck in local minimum that does not correspond to solution of the system of equations. So, so what I wanted to explain is the following. So it's a combination of Newton's method and of steeper descendant. So in one dimension, the Newton's method is very easy to understand. So here is the sketch. I took this from the internet. To remember what the Newton's method is. So if we have the first approximation to our solution, our zero, for example, is x of 1. So we calculate f of x of 1, and then we also estimate the derivative, and we get point x of 2. Then we evaluate function in x of 2. We estimate the derivative. We are sent to x of 3. And then here, at this point, we also know the value and the derivative, and we go closer to 0, and so on and so forth. So extrapolation, by knowing not only the value, but also the derivative. Sorry, is there a question? Sorry, is there a question? Is there a question? No. Sorry. Yeah, today I don't see you. So therefore, I don't know when the question occurs. Okay, so I was discussing this this Newton's method, which probably is pretty clear to you. Now, but this is combination not just of Newton's method, but also steepest descendant method. And steepest descendant method is sketched here. So in multidimensional case, we are solving this problem of first dimension square plus second dimension square plus third dimension square and so on is equal to 0. And then you can think of it as this plot where you're trying to minimize function. And the idea here is that you take a step, which is a combination of moving a little bit in first dimension, a little bit in the second dimension, a little bit in the third dimension, in such a way that the gradient is the largest. So steeper descendant means that you are following the largest possible gradient towards local minima. So this is a combination of taking the step in the direction of the largest gradient, and at the same time Newton's method, which we know well how it works in one dimension, and in general can also be generalized in multidimensional case. But it's well known that Newton's method itself in multidimensional case is not very successful. So one has to combine this with some other things like steepest descendant. So this is a rough understanding of how this multidimensional solver works. Now, what we are going to try this solver on is this function, one-dimensional function, which is tangents minus another function, which is 1 over omega, some constant 3 divided by 1 over omega. So I'm going to evaluate this function. So again, the function is just tangents 2 pi omega minus 3 divided by omega. And first we're going to plot this function, and then we're going to search for zeros. So we're going to plot this function from 0 to 3, let's say, with enough points, with 1,000 points, because we really want to see continuous function where the zeros are. So we evaluate this function on this mesh. And then if we just do that, unfortunately, the plot doesn't look very good. So let me try to do this plot. So PLT plot X and Y. So the plot looks pretty awful because, of course, there are divergences, and this is hard to see anything. Okay, so we don't want to use that. We want to improve the plot a little bit. So as you remember from introductory lectures, there is this fancy indexing where we use this. So we're going to use a function where the value of y is bigger than 50. We're going to create mask where mask will be either true or false on the entries where the y is too big. And then we can use this fancy indexings to set both x and y on these values where the mask is false to none. This is kind of a trick to make sure that the plot routine will not use x and y where the entry is none. So therefore, the plot then appears way nicer. So we don't see divergence, and well, we also use the y limit -5 to 5, but this itself would not cure the problem. So let me show you what appears if we use y limit from -5 to 5. This still shows not only the zeros, but also shows this infinitely steep curve where we go from plus infinity to minus infinity, and we want to get rid of those poles because these are not zeros. These are poles. These are not zeros. So that indexing takes care of that. It's just a nice trick of how to get rid of particular part of the plot, which shouldn't be plotted. Okay. So, and then in addition, we are plotting here with black color. K means black color. We are plotting a line from 0 to 3, and y is 0. So this gives you this black line here. And now we want to find all zeros. This 0 here, the first 0, the second 0, the third 0, fourth 0, fifth 0, and so on. Okay. So once we see the zeros here, then I guess it's relatively simple. We can use optimize Fsolve, and let's see the help for this. Help optimize Fsolve. Optimize Fsolve. And this tells us that what we need to give here is the function, and then next argument is the x0, which is starting estimate for the root, and then possibly arcs. Arcs, we remember what it is. It means additional arguments to the function if need be. Okay, so our f, of course, doesn't have any additional arguments because we hard-coded this value omega c to be 3. So therefore, all we need to do is just give the function f and then some approximation for first root. So first root might be around 0.1. We evaluate this and we get the root indeed at 2.37. Next root is supposed to be around 0.7. Again, we take some reasonable approximation and we get correct root, and then another reasonable approximation, and we get the third root. Now, the problem with this Fsolve is that sometimes we might not get the closest possible root, depending on how the function looks like, but sometimes we can give an approximation pretty close to the root, but the numerical iterations might send us completely out of this range, and we might end up in some solution which is very far away, or we might even get no solution. So this Fsolve does have some drawbacks in the sense that there is no guarantee that we are going to find nearby solution. We're going to likely find it, but no guarantee. So in order to have a guaranteed solution inside the interval, the better method is this so-called bracketing methods, or the methods that take interval in which the solution to zero is being searched for. Okay, so now if we look at the documentation, I hope I have documentation somewhere here, close by. There are lots of, yeah, Fsolve, no, there are others. No, I wanted to find documentation for scipy optimize, yeah, here. So scipy optimize, do you see the scipy optimize screen?
Yes.
You see, okay. So what I wanted to show is that there are lots of root finding routines here. These all those are for scalar functions, in other words, one-dimensional functions. And in this case, in one-dimensional function, of course, you can give parameter a and b, which is the interval in which we force the routine to find zero. Okay, so Thom's 748 is such a routine, which is for Thom's algorithm, and it's very good. Let me explain you why. So here is the nice table of all the routines, and you can see that, of course, bisection is something that guarantees to find convergence inside an interval with the speed of convergence of the first order. So this one means that the convergence is of the first order, of course, because we're always approximating the dependence of the function with a simple line. But then when we go to Brent algorithm, we get better convergence of the order of 1.62 and Ryder 1.41. Thom's method is around is basically the best way, the best rate is 2.7. So this is pretty fast convergence to the correct solution. But of course, this, unfortunately, this cannot support complex numbers. So if you have a function which is complex, which returns you a complex number rather than the real number, then you might use second method, Newton's method, or Helly method. I guess this Helly is probably the best because the rate of convergence is 3 and works on complex numbers. But for our purpose, let's say that we need a solver for real numbers with pretty good convergence, and maybe Thom's 748 is good enough. Okay, so how do we use that? Well, so here I prepared Thom's method, Thom's 748. We use function f, and then we need to give a and b. Okay, now the trouble is that if we just look at this function here, we might okay. So we look at the function and we might say, well, the zero is between 0 and 0.5, maybe. The first zero is between 0 and 0.5, naively. That's what we would say, for example. Okay. And then if we try optimize Stom's 748 between, let's say, some small number f, some small number 0.01 and 0.5, it gives you an error. And this error is that A and B must bracket exactly 1, 0. So the trouble is that in order to use any of those routines, we need to make sure that function f changes sign between the two brackets. And if we evaluate function indeed in these two brackets in 0.01 and 0.5, we see that it doesn't change sign. So that's a problem. Routine cannot work. Now we need to carefully choose brackets in such a way that there's going to be exactly 1, 0 in there. And the issue, of course, here is that the change of sign in such an awful function can occur either through 0 or through a pole. So there are two possibilities. The function can change sign either through a 0 or through a pole here, isn't it? And therefore, we need to be careful when we use this routine that we actually bracket A0. Otherwise, we're not going to get correct solution. So it's a bit tricky. If you have a function like that, using the solver that brackets the 0, it's tricky. So here I found a reasonable set of numbers which do bracket the 0. So 0.01, 0.25, 0.3, and 0.73. And if we use these numbers, of course, we get correct zeros. But just I guess the message is that these functions that require you to bracket 0 are very good if the function is such that you can bracket the 0 with some other previous method. So typically what we do is we use a mesh of points, and then on those points we evaluate the function, we see where the function changes sign, and then we use this more precise method to find exactly 1, 0 in this interval. But the user needs to make sure that this 0 exists. Okay. Yeah, with this, I finished the root finding chapter. And now the only thing that we are left with here is interpolation. And then we can start some non-trivial physics examples. Is there any question about root finding? Any question? No. Okay. So yeah, I don't see you right now, so therefore I need to stop sharing screen from time to time. Okay, let me go back to sharing screen. Okay, so I'm going to discuss interpolation next. So interpolation, of course, is very convenient in scipy because it gives you several nice functions with nice interface. One is so-called Interp 1D, but it turns out that you have even 2-dimensional interpolation with Interp 2D. So 1 and 2-dimensional interpolation. And 2-dimensional interpolation is very hard to do, hard to code yourself. So this is an extremely useful set of routines. Now, how does it work? So we have data X, an array of X of independent values, and then Y, which is a set of dependent variables. We then just create a spline, or we create an interpolation through it, and then we can evaluate this interpolation on an arbitrary set of points in arbitrary point that user wants. So the interpolation is part of scipy interpolate. So we are going to do from scipy interpolate from scipy interpolate import star. So anything that is interpolated is going to be imported. And I'm going to also import from NumPy import random. Turns out that random is again available both in NumPy and scipy. And if we don't interpolate this from NumPy, we're going to get some warnings. This is not errors, they're just warnings. Then I will take here a function to be just sin x, a very simple function. And then we're going to try to interpolate a function sin x with various levels of interpolation. So let's say that we take here on a linear mesh only 10 points between, let's say, 0 and 9. So 0 to 9, we take 10 points, okay? Then x is a good mesh which has many more points, 100 points, okay? So on a very dense mesh, we're going to plot functions so that we see how the interpolation looks like. N is going to be the rough mesh through which the interpolation is going to be done. Okay, so first we interpolate function f of n, and then we add some random noise to it. Okay, which is distributed Gaussian. Okay, so I hear some noise here. Let me mute you. Okay, so so what I want to say,
Professor?
is, yes. Yes.
I think in the top you can get the participants back. Hit more and then show video panel.
Show video.
In your video controls at the top. There's the more button, and then it should say show video panel.
Show video. I see participants. Can you repeat this once more? On the top.
Is there a more option?
Yes. I see
more.
Yes. And then what?
And then it should be show video panel.
I don't have it. Chat, reaction, pause recording, stop recording, meeting, live transcript, breakout room, disable annotation, hide names, hide video, hide floating point controls, share sound, optimize for video clip. I don't have it.
Ah.
I don't know.
Must be an update for Zoom.
Update for Zoom, probably. Something happened and this disappeared. Yeah, well, I guess tonight I'm gonna have fun with this. Okay. Yeah, it's very annoying because I don't see anything what you're who is here and what you're doing. Very unfortunate. I will figure it out tonight. It just changed. Okay, so what I wanted to say is the following. So we're going to write function in this rough points, in this rough mesh, the blue points here. Okay, and then we're going to get a little bit of noise here, like 0.05 of random noise, and we are gonna then see how the linear interpolation looks, how the cubic interpolation looks, and another cubic interpolation which makes the smooth interpolation. Okay, so let me explain what these different interpolations are. So we take function interp1d, and then this produces interpolation, and what is the input to interp1d? Well, the x values and the function values. Function values in this case is our data, which has a little bit of random noise, and on x-axis we have those 9 points. Only those. Well, actually, yeah, I guess 10 points. 10 points from 0 to 9. Okay, so this is our input to the interpolation. And if you do interp1d and you don't specify anything like kind, then this interpolation is linear interpolation. So if you don't write kind, it means linear interpolation. Okay, and then we get an object which is called linear interpolation, and then this linear interpolation can be evaluated at every point. So let me demonstrate this. If we have linear interpolation, then this can be evaluated in every point, like 0.3 gives you a number, but you can also give an array 0.3, 0.5, 0.6, and this gives you an array of y points, which are now interpolations of this function. So what we're going to do here is we're going to evaluate the resulting interpolation on the precise mesh with 100 points. Maybe we can even use a little bit more points because it's going to look nicer. So we do the linear interpolation and display this on a very nice mesh. Then we do the same thing with cubic interpolation, and we display and then we evaluate it on a much more precise mesh. And then we plot those. So here I'm plotting the data, noisy data, with blue, and S means squares. So we have squares, blue squares for the data. Then I'm plotting with the black color, K, the true function, the sign. Then with the red curve, I'm plotting here the linear interpolation through the noisy data. Then with green, I'm plotting cubic interpolation through the data. And then finally with blue, I guess another blue, yes, I'm plotting cubic smooth function. So this cubic smooth is slightly different than cubic interpolation because I'm using different routine, univariate spline. So if you look at the documentation of the two, these are slightly different. Interp 1D is a cubic interpolation that always forces the function to grow exactly through the data. Okay, and that many times it's it's exactly what you want. However, sometimes you have some noise in the data, and you don't want the function to go exactly through the data, and you want to have a parameter which will tell you what is the expected error bar of the data. Okay, and in this case, if you set S is equal to 0 and you say error bar is 0, then it will go exactly through the data, and the two will be exactly the same. So the cubic interpolation and the one with S is equal to 0 are the same, give exactly the same value, exactly the same cubic spline, because we're forcing the function to go through the data points. However, if I make this as non-zero, like 0.1, then the cubic spline is going to try to be more smooth. You see this kind of smoothens everything, and it doesn't go through the points. Of course, if you know something about your data, how big is the error bar, you can use this to kind of improve the interpolation. So I guess our error bar here is 0.05. So therefore, the 0.05 might be slightly better approximation than the naive cubic spline. Okay, so you have several ways of interpolating the data. Now, let's say that we don't have any noise. So we were adding here intentionally some noise to kind of make interpolation slightly more challenging. But let's say that we don't do that. So let's say that we take interpolation of the function fn without the noise. And this is going to be cubic interpolation. And then we are going to calculate the difference between the original function and the cubic interpolation of the function. Okay, so that's what I wanted to do. So look at the difference of the two. Okay, so and at the same time, I want to look at the difference of the univariate spline when interpolation, for example, is also the third order, and I set S to 0. Okay, so as I told you before, this univariate spline and cubic interpolation, interp 1D with kindness cubic, are supposed to give you exactly the same function. So if this is the case, then diff and diff2 functions are supposed to give you exactly the same plot, and this is indeed the case. Okay, so what I'm doing here once more is producing cubic interpolation that goes exactly through all the points. And in one way, in first case, I'm using interp 1D. In the second case, I'm using univariate spline with S equal to 0. Okay, and what we see is that the function sine x and its interpolation through the 10 points is precise up to 10 to the minus 2, 0.025 roughly. So there is an error bar. It's not perfect. Now, how do we improve that? Is there any idea how, if let's say that we have only this 9 points, how do we improve the interpolation? What's the problem with this? And the error bar is actually pretty big still, 0.025. That's pretty large. So what should we do? Any idea? Anybody? Any idea? What would you do? Okay, so two things come to your mind. One is to increase the, we know that sine is extremely smooth function. So if you have extremely smooth function, then higher order interpolation might improve results. This is very simple. So all you do is to change case 3 to case 4, and you look at the fourth order interpolation. And indeed, the fourth order interpolation in this case is way better. You see that this error almost disappeared. So kind of, in this case, the high order interpolation is better. Now, in general, they don't advise, for general function, it's not advisable to use too high order interpolation, because if the function is not infinitely smooth, this might create some problems. So this is not always making a better interpolation. However, what we see as a problem here is there is too much oscillations at the beginning of the interval and at the end of the interval. And this should give you a hint what's the problem. Do you have any idea? Anybody? So why does this huge oscillation occur at the beginning and at the end of the interval? Any idea? Anybody? Okay, so the point is, whenever you see these huge oscillations at the beginning or at the end, this signals that you don't have correct first derivative or the second derivative or the boundary condition. So the boundary condition is not the best. Okay. Now, of course, the trouble is that most of the time you don't know the boundary condition, and therefore this is best you can do. But let's say that you knew the boundary condition. Let's say for sine function, we know the boundary condition, or sometimes when you have a function that you want to interpolate, there is a way of figuring out the boundary condition. And if you know the boundary condition, then you can do much better. Okay. So I want to explain you that there is the third way of interpolating, which is called, a function is called make Interp spline. So I had to Google a little bit to find this particular splining. And so if you do make Interp spline, if you use this one, then it allows you to use so-called boundary condition type 2. So it has an option in which you can input the boundary condition. And with this, you can tune the boundary condition in such a way that, that you can avoid this ringing at the beginning and at the end. Of course, provided that you know the boundary condition. So it supports 3 types of boundary conditions. One is called clamped, another one is natural, and then not a not. So let me explain what these boundary conditions are. Clamped is the one where the first derivative at the ends are 0. So basically, you assume that the first derivative at 0 at the beginning and at the end is 0. So that's one possibility. You can, however, also specify the value of derivative. So you can specify 1 and then a number, and this number is the value of the derivative at the beginning, and you can specify 1 and the value of the derivative at the other end. Okay, so this would specify uniquely the spline. So I guess one thing that I didn't explain is this: the spline function is defined up to 2 extra values. So we need to have at least 2 extra things, like derivative at the beginning or derivative at the end, or the second derivative at the beginning or second derivative at the end, or third derivative at the beginning or third derivative at the end. So we need to specify something, 2 extra information to get precise spline, because otherwise spline is not well determined yet. So there is a natural spline in which we take the second derivative at the endpoints to be 0, or we can also specify the second derivative to have particular number at the endpoints, and finally not or not is the other option, in which in this case the spline requires that the third derivative of the spline is continuous. In other words, the third derivative at x is equal to 0 and in the last point are the same. So it's kind of the third derivative is periodic. So these are the possibilities, and this interpolation with given boundary conditions is of course always better if you know what is correct boundary condition. And in many physics problems, you know something at the very beginning, you know something at the very end. You add these boundary conditions, and then the functions tend to be much better. Okay, so this is it. I think we went through all the lecture notes on scipy, and with this we conclude the introduction to numerical Python. Any question?
Okay.
Professor?
Yes.
I'm guessing you've updated that file since you last updated or last uploaded it to wherever we downloaded it from. Can you upload the copy that you have just presented, if you don't mind?
I will upload it. Yes, I slightly changed this copy when I was preparing for the lecture, and indeed this is not uploaded yet. I will upload that too. Mm-hmm.
Thank you.
Any other comment, question?
Question.
Yes.
So can you interpret more on the S argument in the universal spline class?
Sorry, what's the interpretation of the S argument in this here in the universal spline? Yeah, so I mean, my interpretation is that it's kind of, you should think of it as an error. So how close need to be the spline to the data? Okay. Mm-hmm. Now this is my interpretation actually, because the documentation has, as far as I remember, has slightly more complicated wording. Do I have this open?
Yeah, I checked the documentation.
Okay.
I find I can't understand it. So this is why I ask such a question.
Yes, thank you for asking the question. So yeah, I mean, it is somewhat of a little bit of complicated wording indeed. Again, my interpretation, which might be somewhat wrong, is that basically you can experiment with it. You will see that when S is very small, then the curve will go very close to the data. When S is large, the curve will be pretty far away from the data. So the first approximation is your idea of the error bar on the data. Okay.
Oh, okay. Okay. Thank you.
Yeah. Any other question? Okay. If not, now I prepared the fourth lecture, which is going to be on hydrogen atom. So let me sharing the screen again. Share screen. Okay, so I want to discuss this. I want to show you how to solve Schrodinger equation for the hydrogen atom. This is under in this directory that I gave you. It's it's 04 scipy example hydrogen atom IPYNB. Okay. Unfortunately, I modified this file just a little bit, and I will upload the modified version. But it's pretty close, so you can maybe, when you listen to it, you can maybe correct it. You can enter the corrections. So what we want to solve is the Schrodinger equation, not for a complicated system, but just for an atom. Of course, this can be done analytically, exactly, for hydrogen. and we're going to neglect interactions. So in some sense, we are not going to do anything beyond what can be done analytically. But in the next lecture, we're going to try to add interactions through so-called local density approximation. And this is something that cannot be done analytically anymore. Has to be done numerically. Okay, so Schrodinger equation, well-known thing. So what we're going to do is we're going to use the usual ansatz of the radial harmonics, YLMs. You remember this? These are the usual spherical harmonics, and then the radial part is U of R divided by R. So the reason for this choice, as you remember from the quantum mechanics course, is that if you choose the radial part as U of R divided by R, then the first derivative in the resulting differential equation is absent, and the form of the Schrodinger equation is way nicer. So therefore, this is a good ansatz. And then we're going to also use more convenient units. Namely, R is going to be measured in units of Bohr radia, and energy is going to be measured in units of Rydbergs. Okay, so Bohr radius, as you remember, it has this expression in terms of h bar and e square. My internet seems to be bad. Yeah, and E0 is going to be measured in Rydbergs, which has this expression h bar square root 2 RB. It's roughly 13.6 CV, and of course it's chosen in such a way that the hydrogen atom has a bound state at -1. The first bound state is at -1, minus 13.6 CV. So it's exactly Rydberg is exactly the energy for the bound state of the hydrogen atom, ground state for hydrogen atom. Okay, so once we insert those into differential equation, then differential equation looks very nice. U double prime of x minus LL plus 1 over x squared minus 2 0 x minus epsilon U of x. And notice that there is this 2 here, okay? So in many books or many places, there is going to be no 2. It's going to be just z divided by x, like the Coulomb interaction is 1 over x or 1 over r rather than 2 over r. And this 2 here signals that we are using Rydbergs. So if we used Hartrees, which is twice as big as Rydbergs, then this 2 would be absent. So it depends on the book. Sometimes chemists typically use Hartrees, and there is no 2. Physicists many times use Rydbergs, and we have the 2 here. But again, that only just means that we have slightly different units. Okay, so once we have this Schrodinger differential equation, we can rewrite it in the standard form so that we are going to be able to use the scipy or the int. So we rewrite it in such a way that u is going to be y, our dependent variable, is going to be u and its derivative, and then the derivative of this is going to be u prime and u double prime. And then we need to figure out the boundary conditions. So the first boundary condition, of course, is that value at 0 has to be 0, and that's because the wave function is proportional to u of r divided by r. If u of r close to 0 doesn't go to 0, you see that the wave function would not go to a constant. So it would diverge. So if we want the wave function to be finite at 0, then u of 0 has to be 0. So it's very simple. Now the infinity can also be specified because the function, when we integrate the function psi square of r squared dr, then we see that this u of r divided by r squared, the r squares exactly cancel. So basically the integral is just u square of r dr. And if we want this integral to be finite, then we know that the value in the function in infinity has to go to 0. That's the only way to have a finite finite integral. Therefore, we have the two boundary conditions. One is that the function at 0 is 0, and the function in infinity is also 0. Okay, so these are our two boundary conditions. Now, the trouble is that that up to now we were always able to solve the differential equations if we had all the boundary conditions given at the same point. So we have y, we start integrating, let's say, at 0, and then we need to have both the value and the derivative at 0. Our problem right now is that we don't have the boundary conditions given at one point. One boundary condition is given at one point, and another boundary condition is given at the other point. And of course, in this case, it's much harder to solve the differential equation because we don't have boundary conditions given at the same point from which we can start integrating. So what do we do? What should we do? Any idea? Does anybody have any idea? Yeah, I guess, well, there's explanation down here, which probably you have read already. So the idea is quite simple. It's so-called shooting. We have to use so-called shooting algorithm or shooting method. So the shooting algorithm is more or less, it reminds me of basketball. Okay, so imagine you're playing basketball and you're throwing your ball towards the hoop, and you hope that eventually, with correct velocity, you're going to be able to hit the hoop on the other side. Okay, so you know two things. You know position and velocity at the beginning, and you want to tune the velocity in such a way that that you're going to hit the hoop on the other side. So that's what shooting is. It's very simple. So we have, let's say that we have boundary condition that at the one side, at point A and point B are the 2 points, the two sides. And let's say that u of A is, that we have the boundary conditions u of A is 0 and u of B is 0. Then we do the following. We choose first u of A is 0 at one point, and we choose an arbitrary derivative. U prime of A is C, anything. C can be arbitrary. And then we solve for u of x to the other end, and then we just check what this value of u of b is. Okay, if u of b turns out to be 0, that's great, we found the right solution. But if u of b is not 0, then we need to tune a parameter, available parameters, so long that the value of u of b becomes 0. So in the case of Schrodinger equation, the value in the other end, in infinity, for example, will depend on the energy. So we know that the shape of the Schrodinger equation, or solution of Schrodinger equation, crucially depends on energy. So once the energy corresponds to the bound state, then we know that the function will properly vanish in infinity and at 0. Okay, then it will correspond to the bound state. So our variation of parameter, or the parameter that we need to vary in order to find the bound states, is the energy. So what we're going to do is we're going to start with some reasonable approximation for the energy. We're going to change it until we see that both boundary conditions at A and at B, on beginning at 0 and infinity, are properly satisfied. Okay, so that's the game we're going to play. Okay, understandable? Okay, so now remarks. It turns out that forward integration of the Schrodinger equation is unstable. It is better to start integrating from infinity and then continue down to 0. That's one point. The other one is that it's better to use logarithmic mesh for radial variable rather than the linear mesh, because radial functions need smaller number of points in logarithmic mesh. So this basically, when you code an algorithm, you can check yourself that that indeed logarithmic mesh improves, and we will see now very quickly that integration from 0 up to infinity is extremely unstable. Okay, so here is the algorithm for the implementation. So we're gonna use the integrate or the int function that we just learned how to use in order to solve the Schrodinger equation. We have the boundary conditions u of 0 of 0 and u in infinity is 0, and we're going to use the shooting method to obtain the wave function. We're going to use the logarithmic mesh of radial points for integration, and we're going to start integrating at large distance, such as r is 100, and then we're going to integrate down to r is equal to 0. And we need to start with some derivative, but not too large derivative, because otherwise we might have an overflow problem. Integrate the Schrodinger equation down to r is 0. If your choice for the energy is correct, corresponds to the bound state energy, then we should see that the function at 0 becomes 0. And then we need to search for zeros with one of the root finding routines. Can be Brent Q routine. It can be Tom's routine that we just discussed a few minutes ago. So one of those routines can be used to calculate, to estimate all bound state energies. And in order to do that, we need to start searching for the energy at sufficiently low energy, and then we're going to bracket all the zeros from minus 1.2 times z squared to 0. We know that all bound state energies are supposed to be contained in this interval. Okay, so once we know the bound state energies, we are going to store them, and then once the bound state energies are known, it's actually quite simple. Then we once more compute the solution for the wave function, and once we have that, we could just calculate the charge density. So the final result is going to be charge density for all occupied states. So that's going to be the final output. That's what we want. The charge density for the entire atom, which is the u squared divided by 4 pi r squared. This is the charge density per unit angle, doesn't it? So per unit angle. Yeah, what we need to take into account is that each state with quantum number L can take up to 2 times 2L plus 1 electrons. Okay, where is this coming from? 2 times 2 plus 1? Anybody? Did I lose you? Did I lose you? What is 2 times 2 plus 1? Anybody?
Degeneracy.
The Pauli.
Degeneracy, yes, yes. Which degeneracy? 2 times 2 plus 1.
L.
Yes, so it's orbital degeneracy is 2 plus 1, and spin degeneracy is 2, isn't it? So yeah, so it's spin degeneracy times orbital degeneracy. That's the entire degeneracy of state, isn't it? 2 times 2 plus 1. And of course, some orbitals might not be fully occupied. I mean, in some of the atoms, we have partial occupation of the last shell, and we need to take this into account. Okay, so that's it. We can start coding. Now, yeah, in the past I would be coding in real time, but during COVID I kind of cannot see how you're coding, so therefore I pre-coded everything, and I'm just showing here which I hope is efficient, but I don't know. Okay, so the first step to solve the Schrodinger equation or any differential equation is to code this function that returns derivatives, isn't it? Derivatives. We called it dx in the past, but right now I'm going to call it Schrodinger derivative, which means that given the function our dependent variables are u and u dot, and then this needs to give you derivative of this function y with respect to r, which is u dot times u double dot. Okay, so that's what we need to return. So the input is y, which is u and u dot. The output is going to be derivative of u and the second derivative of u. Okay, then the second variable has to be r. This is the independent variable. You remember last time when we discussed all the int, this independent variable was usually time t, but in this case, the independent variable is r, is the distance, isn't it? So up to here, Schrodinger deriv y and r, we don't have a freedom of changing this routine. It has to look like that. It has to be, it has to have the first argument dependent variable, the second variable has to be independent variable. Now, the rest are optional arguments. L and En are optional arguments, but we need them in this case because we need solution for Schrodinger equation for different L quantum numbers. These are orbital quantum numbers, and for different energies. So we're going to be shooting with different energies, and we need to make sure that energy is correct so that we get the bound state. Okay. So now, given all this L and En, then it's very, very easy to code our derivatives. So the u dot is just the second component. So first we unpack here y, we unpack into u and u prime, and then we return u prime, and then here we need to specify the second derivative. And then if we look here at the equation, we see the second derivative is L plus 1 divided by r squared minus 2z over r minus epsilon. So I guess I didn't put z here because I set z is equal to 1. Now, one important point. We will be solving this equation for generic atom, let's say anything in periodic table. And in principle, you could assume that we need here z, where z, let's say that we are solving a problem with z is equal to, I don't know, 50. And in this case, we will be solving the problem with z being 50. Okay, that's how naively you would do it. Now, unfortunately, we will not. It's numerically extremely hard to get solution with very large z, and the wave functions for large L and large N. Okay, the reason for this is that well, in physics, turns out that larger L and then larger N tend to be screened. So there is an important thing which is called screening in atom. So namely, when you're solving for the outer shells, so for the shells with large N and large L, it turns out that the nucleus, which has large Z originally, is almost entirely screened in the sense that the outer electrons see a way smaller charge of the nucleus than the inner electrons. Okay, so it's completely natural. I mean, we have heard this many times in physics, that the outer electrons in the outer shells see much see the nucleus, which is screened, and you see a very small charge compared to Z. So roughly charge 1 or charge 2 maybe, but not large Z. And in numerics, it turns out that if you use large Z and you try to solve for large L and large N, this is numerically not going to work. It's going to be very hard. So therefore, what we are going to do here is going to assume right now that Z is equal to 1, and we're going to work with Z is equal to 1. Later on, when we are going to take into account interaction between electrons, we will see that actually the Hartree term largely does exactly that. So the Hartree term screens the interaction in such a way, the Hartree term is due to interaction, and it screens the nucleus in such a way that this effective Z never becomes too large. So therefore, when we go to more advanced theory, you will see that this approximation where we neglect Z in this equation is actually pretty good. It's better than if we input Z for heavy atoms. Okay, so once more, I want to justify here why I remove Z and I use hydrogenic-like atom, isn't it? Not atom with large Z. Okay, is it clear?
Professor?
Yes.
What is the value of UP in that function U prime? How are we calculating U prime there? Just by
so yeah, let me just share screen once more. So we are unpacking it. So you see, Y has two components. We assume that Y has two components, and Y has U and U prime components. So in some sense, we need to know it at the beginning. So in the beginning of the interval, the user needs to give both U and U prime. Okay, and then the int will compute U and U prime both at the same time in the next point. And then again, int will compute U and U prime in the third point and the fourth point and so on and so forth. So in other words, U and U prime are bundled together into our dependent variable Y. Okay, but when we need to calculate the derivative of this dependent variable Y, then of course the first component is UP and the second component is this expression. Is it clear?
Yeah, but the function that we would input to OD int we would have to specify what the integrand is, right? So, but in our equation we have U prime U as a function of U double prime as a function of U. So we don't have any relation between U and U prime. Or am I missing something?
We don't have any. Well, look, we decided to work with this. Y is equal to U of R and U prime of R. So this is our variable. Okay, and therefore all we need to do is we need to give dy over dr, which is U prime of R and U double prime of R. So this is our job. Yes. Okay. So let me just begin. Right. Still hard to see. Yeah, that's the idea. So in other words, our variable is Y now, which contains both U and U prime. And all we need to do is to give dy over dr. This is the output, isn't it? Which you know then U double R. This is your input. Okay, so you just copy from the input the first derivative. And all you need to do is to calculate the second derivative. Okay, because that's how it's set up. Okay, so yeah, so what we're going to try to do is just see how to calculate 1s orbital for the hydrogen atom. Okay, so we know that the energy is exactly -1, because the ground state energy is minus 1 Rydberg, and when L is equal to 0, this should correspond to the ground state of hydrogen atom, doesn't it? So what we do is we take some linear mesh, lean space, from some small value to, let's say, 20, and let's say 500 points. Okay, so we are not allowed to take 0 here. Okay, why not? What happens if we put 0? Okay, so the trouble is, you see Schrodinger equation here. You have 1 over r squared, 1 over r. So there are many places where we have 1 over r. Okay, so if we set the first point to be 0, this is going to result in nones. Okay, so we can go arbitrarily close to 0, but we should never touch 0. Okay, why? Because the Schrodinger equation itself contains this 1 over r, 1 over r squared. Okay, very important not to touch 0 ever. Then upper cutoff, we have to know something about the system in order to guess the upper cutoff. I mean, we know that that these wave functions fall off exponentially, so they go roughly as e to the minus r, and so at r is 20, e to the minus r is really small. So this should be good enough. And then we take 500 points, which is kind of already a lot. And we're going to take L is equal to 0, and E0 is minus 1. And then all we do is we use our integrate O de int. The first argument in integrate O de int is the function, which is properly specified here, Schrodinger derivative. Then the second argument is the initial condition, which we're going to say that the value at 0 is 0, and we're going to choose the derivative to be 1. Now, how should we change? How should we obtain the derivative at 0? Because we don't know the derivative is 0. We only know that the value in infinity is 0, but the derivative is not known. Well, if we know analytically the solution, of course, then we know the derivative as well. But the point is that this derivative here can be an arbitrary number. We can specify any number, and we are still going to get the same function. However, the normalization of the function will be different. The normalization of the function will depend on what is our choice for the derivative. So if we choose a bigger derivative, then the function will grow fast, will of course grow faster at the beginning, and this will give you exactly the same shape, exactly the same function. However, it's going to have bigger normalization. And if you choose smaller derivative here, then the function is just going to be normalized to with a different value of normalization. That's all. So we're going to get exactly the same function because we are doing it for exactly the same energy. So we're supposed to get exactly the same function, but with different normalization. So, but we don't care about normalization because we can change normalization anyway. Okay, so we're gonna now just solve the Schrodinger equation with this simple boundary conditions with the derivative being 1. Then we need to give independent variable, independent variables R, and then optional arguments. So optional arguments here, if you go back and look at it, we see that the two optional arguments are L and energy, L and energy. So we need to specify through arcs L and energy, and we gave L equal to 0, energy being -1. Okay, so if we evaluate this, we're supposed to get our function UR. Now, here I want to demonstrate to you that this solution is actually pretty bad. So we are here importing PyLab in order to plot, and matplotlib inline, which plots inline plots, and then we are plotting the first column, which first column gives you u. The second column would give you the derivative of u, isn't it? We don't care about derivative of u right now. We care only about u solution, and we're going to plot the solution here in the plot. And we know from quantum mechanics that the exact solution is proportional to r e to the minus r. So we can compare the exact solution with this approximation that scipy produces. And when we plot this, well, we see the issue. Okay, so the exact solution is the orange curve, and our integration, which was obtained by O the int, gives follows the solution pretty well up to something like 10 or maybe 12, and then it starts to go up. And if we increase the mesh up to 30, for example, we're going to see that this gets even worse. So it really explodes, exponentially explodes. So it's a huge problem. So of course, if we choose the boundary around 12, maybe, then it's not going to be so bad. But unfortunately, this is hard to avoid. And it turns out that this doesn't help even if we if we start with a much smaller r. That doesn't change. That doesn't change anything. So still diverges. So it's not a problem of choosing a bad mesh. No matter what you do, this tends to take off at some point and is diverging. So how do we improve that? What to do? What to do? Do you understand what's the problem? Anybody? Any idea? So
Backwards.
yes, backwards. But what is the fundamental problem here? Why do we need to go backwards? Why is backwards much better than forward? Well, in order to understand that, it's a good idea to recall our method on calculating Basal functions. You remember this Basal function issue? So in Basal functions, we understood that if we iterate forward in some regime where n is where x is much bigger than n, as far as I remember, so the value of the Basal function would get smaller and smaller and smaller. So each value of the Basal function would become exponentially smaller than the previous function. So for example, order, let's say Basal function 20 was small, but 21 was exponentially smaller than 20, and Basal function 23 was even smaller than 21, 22, and so on and so forth. So each Basal function was way smaller than previous one, and we had to calculate some very, very small number from previous number, which was bigger. Okay, and in order to get this, in order to calculate next value with recursion, there was a large cancellation between numbers. Okay, this large cancellation is numerically, of course, extremely unstable. So large cancellation always leads to huge error. And look, if you look at this curve, you see that cancellation is essential. Why? Because we need to have a value. Let's say we start around 5. We need to have a value at 5, and we need to have derivative at 5 in order to calculate the value next to it. Okay, and it's obvious what's going to happen. I mean, you will take a value which is already small. You will take the derivative, which pushes you to even smaller value. So you're going to subtract two numbers which are very close, and you're going to get an exponentially smaller number, and so on and so forth. So you need to climb here towards numbers which are extremely small, and these small numbers can only occur by very, very delicate cancellation of numbers. Okay, so to understand this even better, I wanted to show you here the plot of so-called Euler's method. So I didn't explain yet how the inner working of the O the int is, and we're not going to go into details. But this Euler method is the simplest possible method for solving differential equations. Of course, in practice we don't use that, but it's the simplest thing to demonstrate the working of the method. So how does it work? Let's say that your blue curve is the function that you want to calculate. This is the solution of your Schrodinger equation, or solution for differential equation. What you do, what you know, however, is the value of the function at the beginning and its derivative at the beginning. So therefore, you can, with knowing the value and the derivative at point A0, you can make one step, which of course you can tune how big the step is, but let's say this is the step delta H, and this gives you a value at some later R, or bigger R. And then you are given the routine in which you can calculate the next derivative. Once you know the derivative, you can make another step, okay? And again, once you know the derivative here, you can make another step. You know the derivative, and make another step, okay? So now, when this function, when this value is here, become exponentially small, like we discussed here. So when they become exponentially small, we know that the value from before and the derivative will need to push you to a number which is exponentially small. And number which is exponentially small can occur only by cancellation of bigger numbers. So you subtract two numbers which are very large and you get cancellation. Okay. Now the Runge-Kutta method, which is basically used in this ODE-int, is a bit more complicated. So the approximation is not as bad as in Euler's method that I just presented. So what we do there is we take the value of the function and its derivative at the beginning, but then we also evaluate the derivative in the midpoint and the value in the midpoint. And so we first make one Euler step, we correct the value in the mid step, we take another Euler step, and then we correct another Euler step, and I think we then go back and we use this second Euler step to this value, and this is finally we take an average of this, as far as I remember, and then we get much better approximation for the value at the end. So it's a bit more sophisticated method and more precise, of course. The error bar is the fifth error, h to the 5, but the point is it still uses this type of steps to evaluate the value down the road by estimating the value, by estimating the derivative in previous points. And when large cancellation occurs, then we know that there is going to be a problem with numerical error, and that's what happens here. And you know, yes.
So this is the same sort of issue, it looks like, that you have with like the Newton-Raphson method with horizontal asymptotes, where you end up wildly overshooting or undershooting. It's the same kind of thing because of the really tiny derivative.
Yeah, well, it has indeed.